This course will take you from zero to hero in programming with C and Visual Studio on Windows. This course is packed with coding sessions, with best programming practices, how to make the best use of Visual Studio, and much more. Do you want to learn how to program but not sure how to start or even where to start? Do you want to start a successful career as a computer programmer? Do you want to be able to look at code and quickly understand what it does? Do you want to become a better programmer? Do you want to build desktop applications, mobile applications, or even games? Do you want to be able to read or modify C code with confidence? Do you want to become a world-class software engineer? Do you want to earn top dollars? Do you want to take your career to the next level? If you said yes to any of these questions, then this course is for you. We will cover computer basics. We will cover programming fundamentals. I've dedicated a full section on becoming familiar with Visual Studio. We will cover the basics of C, control flow in C. We will learn pointers and arrays in C. I've dedicated full sections on both pointers and arrays, making sure that you avoid the pitfalls of pointers and how to become very comfortable with pointers in C and C++. We will cover strings in C. We will cover functions, recursion, dynamic memory allocation, how to avoid memory leaks, and how to avoid problems when working with low-level memory in C and C++. We will talk about structures and unions, enumerations, file I/O. We will look at debugging in C, a section on the most important preprocessor directives to learn about in C. We will even build our own static libraries in C. We will also work with multiple projects in Visual Studio and more. So taking this course will definitely help you become a better programmer.
So the first thing we want to understand about the computer system is that it is composed of two main things. First, the hardware. And the main parts of the hardware are the CPU and GPU, memory, and storage. They usually come on the motherboard, which is the main circuit of the hardware. In addition to the motherboard, there's also some additional peripherals like input-output devices. For example, the mouse, the keyboard, monitor, and the printer are considered peripherals. The second component of a computer system is the software. And here I list three different types of software. First, the BIOS or firmware. BIOS stands for Basic Input-Output System. The second important part is the operating system. Without the operating system, our programs cannot run. Programs are written in a programming language and then translated to machine code that is understood by the computer hardware so it can be executed. Alright, so what is the CPU? The Central Processing Unit is also known as the processor or the brains of the computer. It's responsible for executing programs or instructions. Modern PCs and computer systems have multi-cores, more than one processing unit. So for example, dual-core, tri-core for 3 cores, quad-core, etc. The CPU is composed of the following components. First of all, something called ALU, Arithmetic Logic Unit, responsible for performing arithmetic and logical operations. Addition, subtractions, and comparison is done by the ALU. The second one is called the Control Unit. This one extracts instructions from memory and tries to decode and execute them. In addition to these two components, there are two other components we need to mention. Registers. This is a small amount of memory available to the CPU, and it's part of the CPU itself. It's much faster than the main memory. The CPU uses this to cache and store some variables that are important for execution. For example, like where is the next instruction to be executed or run by the CPU. That usually is stored in a register. The second level of memory that's similar is called the cache. The cache memory in modern CPUs is used to reduce the average time to access the data from the main memory. Instead of traveling through the system bus to the main memory to fetch the data every time, now the modern CPUs actually have a cache system that actually can cache data and instructions that are most oftenly used, so that it's faster for the CPU to access them. Another thing to consider, understand, is the difference between 32-bit versus 64-bit. There are different types of processors that sometimes are referred to by the bit numbers of how much memory a CPU can hold in its registers. The maximum memory address a processor register can hold is often a key indication to say, like, oh, this is a 32-bit system or a 64-bit system, or it could be an 8-bit system, 16-bit, etc. what is the maximum memory address that can fit and hold in a register for the CPU. So if a CPU is 64-bit, that means it can hold up to 8 bytes in a single register. If it's a 32-bit, that means it holds up to 4 bytes in a single register. If it's an 8-bit system, that means it can only hold 1 byte address in a single register. Now 32-bit processors can only access up to 4 gigabytes of memory because it's only 4 bytes, 2 to the power 32, a maximum of 4 gigabytes of memory. Whereas a 64-bit processor can access way more than that, 2 to the power 64. So like nowadays there are a lot of systems that have 64 gigs, 128 gigs, 192 gigs, maybe more. In addition to that processor, there's also a note about the operating systems themselves. Because of the fact that there's 64-bit processors and 32-bit processors, operating systems can take advantage of that. A 64-bit operating system can run both 32-bit as well as 64-bit software, and it can harness the full power of the 64-bit processor, whereas a 32-bit system can only utilize a subset of the processor, even if the processor is 64-bit. Another component that's important is called the GPU, or Graphical Processing Unit, also known as the Visual Processing Unit. This is a special circuit chip that can help accelerate the processing of images and output them to display. There's a lot of systems out there, including mobile phones, embedded systems, game consoles, that have a dedicated GPU, which means that it will release the main CPU from having to process computer graphics and images. That's a more efficient use of the system. It can also be present on the motherboard of the system, or it can be an external on a video card.
Okay, so as a summary to this lecture, we discussed the CPU and its components, and also we discussed the GPU and how it can process the images faster than the CPU. We also discussed the 32-bit versus 64-bit processors and how the operating systems can utilize the power of the processor. In the next lecture, we're going.
Alright, next is the memory. So the first most important type of memory we need to know is the random access memory, or RAM. Any byte of memory can be accessed directly without touching any other byte given its address in memory. That's why it's called random access memory. It can randomly access any byte or any location given that you provide that location. It's the most common type of memory in computers and other devices. It's also known as the main memory. So when somebody refers to the main memory, you need to allocate memory or you need to use the memory. That's meant by the random access memory. The main memory, or the RAM, is temporary storage. That means that all data will be lost if we reboot the system or if we power down the PC or device. The second type of memory that we need to know about is read-only memory, ROM. The ROM chip is used mainly for BIOS and firmwares. Once you write data to it, it cannot be removed and can only be read after that. And even if you turn off the computer, turn it back on, the data will still be there. This is needed by most motherboards and hardware systems to boot up. ROM is known as non-volatile, whereas RAM is volatile because it loses its data. Alright, now we want to talk about an important subject, which is addressing memory space. In the addressing memory space, as you can see in this diagram here, each data element has an address. Each byte of data has memory location that can be read or written to given its address. A byte is an 8-bit of data, a bit is either 0 or 1, and a single byte can hold a value from 0 to 255. Now a byte can be signed, unsigned, all that details we can skip for now and we can focus on it when the time is right in the future lecture. Memory addresses are of two types. They can be physical addresses, and the physical address, the direct address of the memory location, is restricted to system software like BIOS and operating system. Typically, it's only accessed via machine code through the operating system code itself. The second type is called virtual addressing. Virtual addresses are usually given to our programs by the system software like the operating system, so that your program needs memory and it asks the operating system, hey, give me some memory so I can execute my instructions or store my data. The address that the system gives to our programs is usually virtual address, unless we have some special programs. But I'm talking about in general, programs will use virtual addresses because the operating system will hand you that virtual address. In this case, why is this useful? This is useful in many ways, some of which is that your program doesn't have to worry about whether this is RAM or disk, because if the operating system or the memory manager part of the operating system hands you the memory, if you run out of real RAM memory, then it can actually virtualize it and it can use the disk as a slower type of memory, but at least your application is going to continue to run, is not going to crash or stop running because of out of memory situation. Okay, so now we want to move on to storage. It's also known as the secondary storage. There's two types that we need to know of. The hard disk drives, these are slower but bigger in size and cheaper than RAM, and you can save the data on them even after you turn off your computer system. So that's the first type. The second type is now called flash or SSD, solid state drive. This one is more expensive than the hard disk drive, but it's faster and it's quieter too. Continuing on storage, we're going to try to see how to access certain parts of the storage using code, either to read or write information. We will look into that in more detail when we get to a section about working with files and persisting data to disk later in the course.
Okay, so as a summary to this lecture, we discussed the memory and the main types, which are the RAM, the main memory, which we said is a temporary memory, and then we discussed the ROM, which is non-volatile and does not lose its data. Then we also discussed the difference between physical and virtual memory addressing. And then we touched base on storage, the two types that we care about, the hard disk drive and the flash, and how we can utilize that for our programs in the future. In the next lecture, we will talk about software.
Okay, so now let's cover the operating system, or the OS. Like I said before, this one manages the computer hardware and software resources, and it provides services for our programs. The OS is the component of the system software that the application usually requires so that it can function properly. So now, what is a computer program? So this is a definition that I usually like to use. It's a set of instructions like we see here on the screen. A program is a set of step-by-step instructions. It has a starting point and then it starts executing, and these instructions are written in the language understood by the computer system or the device. So usually programs are in binary format, composed of binary zeros and ones. How do we write programs? We often use programming languages to write them. Thank God we don't have to deal with zeros and ones like in the 1940s, 50s. Okay, so as a summary of this quick introduction, we discussed that we have the CPU that has registers and cache. The CPU is the processing unit that has the ALU and the control unit. See how registers are attached to the CPU? That means they're the fastest kind of memory because they're very close. And then after that comes the cache, and there's multiple levels. You can read up on that. And then there's the main memory, and we mentioned the physical and virtual memory addressing. After that, we look at the secondary storages like the drives, the hard drives, the SSDs, etc. So this is kind of a diagram of how the computer system is tied together, and some peripheral devices in here, keyboard, mouse, etc. Another summary to recap is that we discussed both the hardware and software components of the computer system. We discussed the operating system and the programs. So just to leave you with this as a takeaway from this whole lecture is that our programs are usually stored on a disk or a flash, right, on a persistent storage. Then they need the RAM, the temporary storage, so that they can store their data, they can execute instructions. The CPU is the brains of the computer. It knows that you need to load a program from disk, so it loads it from disk for you into RAM, and it allows this program to communicate with the RAM and the disk and execute some instructions. This is kind of the whole idea of this section, is just to understand the relation between these three. Once you understand the CPU, the RAM, and the disk relationship with our programs, the machine code, and the operating system, then we should be ready to move on to the next lecture. Alright, so in the next lecture, we're going to get a closer look at programming language.
In this lecture, we will cover the definition of a programming language and the different types of languages that are important, and understand the difference between compiled versus interpreted languages. You will understand the meaning of a programming language and learn about the different types of languages and their use. This lecture is for absolute beginners, so if you have programmed before, you can skip this lecture or you can continue watching. So let's get started. So what is a programming language? A programming language is a notation for writing programs that can be executed or run by computers. Different languages have different purposes. Some types are like machine languages. These are interpreted directly in the hardware. So the machine language is the lowest level. It's like the exact code that the computer or device will execute. So as an example here, we have the machine code for an Intel 64 architecture machine language. As you can see, it's just a series of bytes that are understood by the CPU, can be decoded and executed by the CPU. Okay, so the next level up is the assembly languages. It's simply a thin wrapper over the corresponding machine language. So it's kind of like a one-to-one mapping. Like assembly language can be translated to like one machine code or maybe a series of 1 or 2 or 3 machine codes. As you can see with this example, moving one value to another value, jump if not 0 to a label somewhere in the code. So it's really a very simplistic language. As we learn C, you will find out that this whole stuff can be done in a single simple statement in C, for example, or even the high level languages. But this is the idea of an assembly language. It's like a one step above the machine code, something that as humans we can read and understand. Right, so moving forward, the next is called high-level languages. These are completely machine independent. They're closer to human language and further from the machine language. So examples are like Java, C#, C, and C++ are all considered high-level languages. They have names for almost everything, variable names, type names, functions, constants, etc. They also have certain control structures that allow you to do conditional coding. You can compare things, you can loop and iterate through things. You can define your own types and structures. Classes exist in the object-oriented ones, but for C specifically, C is not an object-oriented language. There are no classes there. The other languages like Java, C#, and C++, these are considered object-oriented languages, and they have the notion of a class. But C has everything else in here except for the classes. Exceptions are also another feature of these languages. Okay, so the next kind or type of languages is the system languages. These are designed for writing low-level tasks like memory and process management. So C is considered both a system and a high-level language. When you hear somebody saying, oh, this is a low-level thing, a low-level task, a low-level program, then think of C and of the things that it allows you to deal with. For example, system languages allow you to deal with memory management, process management. Process here means program, and that's enough of a definition for now. Data transfer, caching, device drivers, even operating system level stuff like writing the kernel of the operating system. C was actually originally invented just so that most of the Unix operating system was rewritten in C. Next higher level is called scripting languages. These are generally extremely high level and powerful. Two examples I have here, the JavaScript and Python. The difference between these and the high-level languages like C# and C++ and C, this is considered a dynamic language. So the same thing is for Python. The last thing we want to touch base on is the difference between compiled languages and interpreted languages. Compiled languages, the name comes from the fact that when you write the code, you need to go through a process called compilation of the code. You need to compile your code. During the compilation process, before you run the app or the program, the compiler will try to find any syntax errors, any problems with your code, and it will not actually compile successfully until you fix all the syntax errors and all the code mistakes. That's why it's called a compiled language. The nice thing about compiled languages is that you know ahead of time what kind of errors you have and try to fix them. And also, it actually allows the compiler to generate machine-specific codes. So that's the advantage of a compiled language. The next type is the interpreted language. The idea is that your code, source code, is translated during runtime. When you run the app, when you run the code, the interpreter starts looking at the code line by line or statement by statement. At runtime, it tries to translate it and try to execute it. The problem with this approach is that you might be surprised with some runtime errors, right? Something that a mistake or you forgot to do something. That kind of stuff is discovered at runtime late in the game. Whereas the compiled language, you capture these early on by the compiler. The interpreted language is done at runtime. The nice advantage of that is that the machine code is platform and machine independent, meaning that it translates it at runtime depending on the environment it's running on and executes based on that. The other disadvantage of an interpreted language is usually slower than a compiled language because the process of translating from source code to machine code happens at runtime during execution, versus the compiled language, that translation happens one time at the compilation and then you end up with a running executable that you can run immediately when you want to run it. Okay, so as a summary, to recap, we said that C is a high level and a system level, meaning low level programming language. It's a very powerful language. You can do both low level and high level stuff using C. The nice thing about high level languages are they increase your productivity. C is a compiled language. It's not an interpreted language. The compiler is very useful at catching syntax errors early on. The compiled code is machine processor specific. So that's basically what we touched base on in this lecture. I hope this is useful so that you can move on with the course. Alright, so next we're going to touch base quickly on the C language history. In this lecture, we will cover how C language was created and go over the different versions of C standards and understand differences between them. You will understand what versions of C are available and what standards mean and which one we will be using in this course. So you can skip this lecture if you have programmed before, or keep watching if you're interested to just learn a bit of history about C. The origin of C. Dennis Ritchie developed C between 69 and 73 at the AT&T Bell Labs to rewrite most of the Unix kernel. ANSI C was standardized by the American National Standards Institute back in 1989, also referred to as C89, also known as Standard C. So whenever somebody talks about Standard C, you have to know that we're talking about the C that was standardized back in 1989, C89. It was adopted later by the ISO standard, referred to as C90. If you say C89, C90 is kind of the same, which is a cross-platform and supported by most modern compilers. Other versions and other standards of C that came out later, in 1995, the C95 was another standard, added minor amendments to the C90. Support for international character sets was added back in the C95. In the 1999, the C99 was also standardized. It added several new features like inlining functions, several new data types, also added support for single line comments the same way in C++. This is an example of a single line comment. Even if some compilers may not choose to be a C99 compliant, they actually would support this as an extension. In 2011, it was also known as C1X. There was another ISO referred to as C11. It replaces the C99. The main reason for it was to standardize some of the features that started showing up in modern compilers. Okay, so in this slide, we want to talk about how Visual Studio handles the C language. All versions of Visual C and Visual Studio supported only C89/C90. Visual Studio 2012 was the first to add support for C99 as well. And newer versions of Visual Studio will keep adding more and more improvements, and C99 was added to Visual Studio 2012, and then in 2013 improved that significantly by adding additional support. Visual Studio 2015, there were further improvements added to the Visual Studio compiler. So again, in this course, we will be focusing mainly on C89, C19 standard, which is referred to as Standard C. As a summary for what we discussed, C89, C90 is supported by most modern compilers. We will be focusing on the feature set of this standard in this course. Most compilers support this standard. The Visual Studio C++ compiler will support everything we will teach in this course. That's why I recommend using the Visual C compiler. In the next lecture, we will go over how to install and configure Visual Studio 2015